In this video, we are going to learn about the Bert model. So first we will talk about the transformer, just a quick recap on it, and then we will talk about two main ways of applying some sort of a representation, such as the representation we got from Elmo, for example, or the one we will get from Bert. How do we apply it on a downstream task like sentiment analysis or some task like question answering and so on. Okay, and then we will talk about the closed tasks. You will get to see what this is because it inspires some of the work that's done in Bert itself, how Bert works. Okay, so these are the four main things that we will talk about here. Before I start, let me give you a very high level summary of what really Bert is, okay? So Bert basically is composed of two things. So let's say that I have a sentence, and this sentence has some tokens. What Bert does is it will take some of these tokens and it will mask them. So let's say we take this token and this token, and then we just replace them with the word mask, literally speaking. Okay? And then now the model will try to predict what these words were. Okay? So we train the model to predict the masked words. And this is why we call it a masked language model. Okay, so MLM. Okay, this is different from other language models we have seen before that try to predict what the next word would be given the history, right? So that's the first task that Bert is trained on. The second task is basically called a next sentence prediction task. So let's say again I have this sentence. Okay, let's call it sentence A, and then it has these tokens. Okay, 1 to n, and then I now have a sentence, but I don't know if this sentence is really in the original data. I don't know if it was really the sentence that came after sentence A. So this is sentence B, okay, and sentence B, if it was the right one that really came after sentence A, then we would just put a check mark, say okay, so okay, fine. But then one thing we could do is we could have sentence B bar, which is basically a sentence that never occurred after the first sentence. And so now the next sentence prediction task is basically given a sentence, asking whether this sentence is a good next sentence or not, right? So if it is this specific one, yes, it is a good one. But if it is this specific one, no, it's not. And how do we do this? Well, we just take a data set. Each of these is a sentence, right? And let's say this was our first sentence, sentence A, and this was our sentence B, right? This one. So in this case, this will be a good sentence. So sentence B here did occur after sentence A. But we want to train the model as a binary classifier such that sometimes we also have sentences that can't be good sentence B. Okay, so we go to if this data came from Wikipedia, and this was like article, let's say about Barack Obama, for example. Okay, and sentence A and sentence B came from this article. So let's pick another article from Wikipedia. Now, let's say this article was about Vancouver, and it has its own sentences and so on. And I would randomly take any sentence. Let's say I take the sentence and I put it here. Okay? And this can, let's call it sentence B bar. It can't really be a good next sentence because it came from a random article. But basically, that's the whole idea. We trained Bert on a task called next sentence prediction task, where sometimes we feed it good sentences, sometimes we feed it bad sentences, and we get these bad sentences as randomly sampled from some sort of a different article, for example, in the data. Okay, so that's basically what BERT is, like a masked language model and a next sentence prediction model, and it does these together. So it's pre-trained on this task and this task simultaneously. Okay, let's go back to the slides. So that's the paper, the BERT paper, and it's based on transformers. BERT is basically a transformer encoder, right? And since when we try to predict these words, the masked words, we will depend on right and left context. So we call it a bidirectional transformer. And basically it's a deep neural network, so this is why deep is there. And we call this whole thing pre-training because we take a data set like Wikipedia, for example, where we don't have specific labels. So Wikipedia is not a data set for sentiment analysis. It doesn't have labels for sentiment analysis. It doesn't have labels for question answering. It doesn't have labels for named entity recognition. So it's an unlabeled data set, but we can take it and then we train BERT on it. And now BERT gives us a powerful representation. And then we can use this representation, plug it into a downstream task like sentiment analysis or question answering. And we perform the learning. And at that point, that learning is basically, we're taking the pre-trained, now we call it pre-trained because it was actually trained on just a general task, right? We take the pre-trained BERT and then we fine-tune. We say we fine-tune it on the downstream task. By fine-tune here, we mean like we take it and then we use it on a labeled data set, for example, and then we perform as a classification. So by doing that, we are fine-tuning it on the labeled data set, like sentiment analysis, for instance. Okay, so it will have a pre-training stage. So BERT is basically going to be the retraining thing, but then we can take it and then we fine-tune it on a downstream task. Okay, and we will see what fine-tuning is. Okay, before going to BERT, let's look at the transformer quickly. The transformer had an encoder, which is this part, and it also had a decoder, which is this part. And the important thing to remember is that each of them had a number of blocks. So this whole part here was one block, and we can repeat it several times. So let's say we repeat it 12 times, for example. Each of these blocks is we can say a block or a layer. So this has like L is equal to 12 here. If this N is 12. So because basically what we will do is we will take this block, okay, and then we repeat it. We have many of it. Okay, paste this image here and then paste it again. So for example, here now we have 2 blocks. Okay, we have 3. And BERT, as a transformer, basically at the encoder side, it can have, an n number of these layers. Okay, and that's like, how many layers there are. Okay, and at the decoder side, it can also have multiple of them. And each block is composed of 2 sublayers. One sublayer is a multi-head attention. The other is a feed-forward neural network. And around them, we do some adding and normalization and so on. So feel free to refresh your own memories about what these are by going back to the lectures on the transformer. Okay, so Bert is a transformer encoder, basically, and it has two main ideas. The first idea is a masked language model, which I talked about, and the second one is a next sentence prediction. And once we pre-train Bert, okay, so that's like the first part of it. Like we pre-train it, and we pre-train it on two tasks, this task and this task. We can now fine-tune it on a downstream task, and I'll show you what this means and how we fine-tune it and so on. Okay, but okay, we pre-train and then we fine-tune. Fine. What is the architecture of BERT? Well, we said it's a multi-layer bidirectional transformer encoder. Multi-layer, it means like we have an n number of, or an L number of layers, you know, or each layer is just one of these transformer blocks, as I mentioned, and it has like a hidden dimension of a certain size, and it also have, because it has multi-head attention, so we can have a number of self-attention heads, you know. So they train two BERT models, a smaller one, they call it BERT base, and a bigger one that's BERT large. The smaller one has 12 layers. The hidden size is 768, and it has 12 attention heads. Okay, if you multiply this by this by this, you will get roughly 110 million parameters. Okay, the large BERT is trained on 24 layers, 1024 hidden dimensions, and then 16 self-attention heads. And again, if you multiply this by this by this, you will get roughly this number, 340 million parameters. Okay, so it's quite large, and you know, of course, the large one is much more powerful than the smaller one, right? Okay, that said, they talk in the paper about two main approaches, and then they criticize both of them, and then they build on top of that. They just trying to motivate Bert. They say, okay, something like Elmo, we can think about it as a feature-based approach to applying a given representation on a downstream task. Now, the idea here is that, you know, Elmo and Bert, for example, these are models that try to learn a general representation of language, right? And then you use each of them on a downstream task. But in the case of Elmo, you train it, you get some representation, and then you take that representation and then you add it to a downstream task representation. So let's say we have a task like sequence tagging, and now you have an Elmo representation that you have learned on a dataset, let's say Wikipedia, and then you take that Elmo representation and then you concatenate it to the downstream task representation at the first hidden layer. Okay, so you take each H, so from H1 to HT, for example, these are the hidden units in your Elmo, okay, and then you concatenate it to the first layer hidden units, as we have seen in the previous lecture. By doing that, you are basically trying to enhance the task-specific representation with the Elmo representation, and that should give you a better overall sequence tagging system. So they call this process here a feature-based approach to applying a representation on to a downstream task. There's another approach that they refer to as fine-tuning, and fine-tuning, Bert actually uses this approach, which is like train a general representation and then use it. Use the whole representation. Don't concatenate it to the downstream task. Just use the same representation, just enhance it a little bit. Like continue learning using it on the downstream task. So now you have a representation, and then you have a labeled data set, let's say sentiment analysis. Now start your sentiment analysis model with this already learned representation, with this already pre-trained model, and now you are going to fine-tune the weights of that model on the sentiment analysis data set using the sentiment analysis labeled data. What this means is that you have a model that's pre-trained with some parameters, and now it was trained on general Wikipedia. It didn't know sufficiently enough about what sentiment analysis is. Now give it a sentiment analysis data set, tell it these sentences are positive, these sentences are negative. Now fine-tune the weights of the model just using this labeled data. That's what fine-tuning is. And there was this model from OpenAI that's basically a transformer model that's generative. It's already pre-trained and it's used to fine-tune. It's used for fine-tuning, the same way Bert is. But this model was basically what? It was basically a language model that is able to, it's a unidirectional transformer model that is able to generate words. So at each time step, it's gonna generate a word based on what it has seen before. Basically, you can take that generative model and instead of using it to generate words, just use its representation. And then fine-tune this representation on a downstream task. What this means? Well, if you have a language model and you are here and you want to generate the next word, okay, now instead of generating this next word, I mean, this model, after you train it, it has a good representation. And by a good representation here, we mean like in order to actually predict what the next word is, you're going to have a softmax over your vocabulary, right? Over V, over the vocabulary. And the most likely word, you're going to choose it here and so on. Cut the model before this last layer. So, so the model before this last layer, the layer before this last layer is a good representation. Let's say it was a fully connected layer. Take it and then now use it with the sentiment analysis data. Just fine tune it a little bit, okay, and then do the sentiment analysis with it. That's a fine tuning approach. All right. I hope this is sufficiently clear. The point of criticism they have here is that, well, really, this Elmo model and this OpenAI model, they are both trained unidirectionally. So they are unidirectional model. So definitely the OpenAI model is trained from left to right. It's a unidirectional transformer. Elmo is trained with a BiLSTM, but really it's a superficial BiLSTM. So we have a left to right and a right to left, and each of them is trained independently, and they are just concatenated after training. And what the Bert paper is saying here is that that's actually not ideal, because you trained each of these LSTMs independently, and you just concatenated the representation after you train. How about we actually learn from both directions in the same time, simultaneously? Okay, so that's something that Bert will do. So they criticize the unidirectionality, because they say here that it's actually suboptimal. It's desirable to look at both directions, and it's desirable for some tasks like question answering, for example, or sequence tagging, right? So if I have, so let me give you the example of a question answering. So if I say I went to the class because I wanted to learn. Now, if I'm here, if I have seen this part, if I ask you a question and say, why did you go to class? Right? You only have seen the history, you have seen the past, you haven't seen the future. So you don't really have an answer to the question. And what they are saying is that a model that really looks at both directions should relate, you know, learning to going to class. Okay, and so they are saying this is useful when you pre-train a model, pre-train it bidirectionally. They are saying this is also useful for something like sequence tagging, for example, right? Because sequence, if you're doing named entity recognition, uh, and you have something like New York City, right? If you are here, it's useful to have seen the word new, but it's also useful to actually look at the word city. It's also a useful piece of information to know that New York is a location, okay, as a single unit. Okay, yeah, fine. One more thing that we just need to talk about, because it inspires some of the work in Bert, is this closed task. So this is basically a task. This work comes from Taylor, but I'm just showing you a paper, a more recent paper that puts together a data set for the closed task. Um, and the closed task is basically a task that requires filling in missing words or sentences to best fit the surrounding context. What does this mean? Well, let's look here. And this is a sample from this paper. It's a closed task dataset from teachers, so they call it cloth. So basically, you have a passage, and you go ahead and remove some words. You remove this word, and you ask a learner, what was the word that is removed? I'll give you 4 choices, and now it's your role to tell me what is the word that best fits. And the answer is excited here. Okay, so Nancy had just got a job as a secretary in a company. Monday was the first day she went to work, so she was very, very what? That's the question. And arrived early. So the best answer is very excited. Okay, and you do this with all other examples and so on. And the idea is that Bert gets inspiration from this because they will now mask this word and mask this word and mask this word. Okay, so for each of them, they really would put like some token called mask, and then they will train the model to be able to identify what this word was, what these masked words were. Okay, so that's the masked language model task in Bert. Okay, and as I said, it has 2 components. So you can, once you pre-train it, you fine-tune it on a downstream task. And when you pre-train it, you just take like an unlabeled data set like English Wikipedia, for example. I think they also train it on another data set. I think it's like a book corpus. So 2 large data sets. They don't need to be labeled for anything. They are just all what we need to do is we take each data set and then we mask some words, right? And then we can take the for each given word, we can take the next sentence for each given sentence. We can take the next sentence and we try to learn whether it's a good next sentence or not. Sometimes 50% of the time we swap the next sentence with a random sentence, as I said before, and then we learn. So we don't need these data sets on which we will train Bert to be labeled at all. This is in fact what we call self-supervised learning. By self-supervised learning, we mean that we have a way to take an unlabeled data set and then learn from it without need to any labels. And this is easy to do in our case here because we just remove some words from the data and we put masks. So we turn it all of a sudden into a labeled data set because we know what these masked words were, but we don't do this labeling manually or anything. It's an automatic thing. So this is why we just say it's self-supervised. Again, people will still refer to it as unlabeled, but it's really self-supervised. It's self-labeled. We can create the labels from the data itself. Okay, so that's like masking is possible to do, and also the next sentence prediction part. We don't really need to manually prepare next sentences. We can just, for each sentence in the data, we can take the next sentence, we consider it the label because we know it occurs. So we can say, is this the next sentence or not? And 50% of the time, we just randomly put you randomly pick sentences from a different article, for example, and then we put it there, and it's gonna be the wrong answer, the wrong sentence. So in this way, we self-supervise. We all of a sudden turn an unlabeled data set to a labeled to a data set that is labeled. So that's self-supervision. So Bert does that, and they call it pre-training. And then once we pre-train, we just plug it to a downstream task to fine-tune the model. So we kind of like have a model now. The model has certain parameters, but let's say it was not trained on sentiment analysis, as I said. If the sentiment analysis is a downstream task, then now we have a data that has sentiment. Then we sort of take the model. Then we continue training it on the downstream task to tune its parameters. So that's the fine-tuning part. Okay. Let's talk a little bit more about Bert pre-training. Okay. Let's not look at the illustration now. Let's just first look here. We take certain words and we tokenize them with a tool called WordPiece. So this is really a tool that would take a word like hello, for example, and it would break it into HE and then LLO, and it would put like some hash sign, 2 hash signs here, just to show that this string really did not occur on its own. It has something that preceded it. So we took the word and we break it into this token and this token. So this is like, we refer to it as byte pair encoding. Byte pair encoding, okay? So now when we do this, we can work with a small vocabulary because by splitting words into these tokens, we will get like a lot of we will be able to capture a lot of words. The representation is basically based on this subword component that such that lots of words will be able to be captured by these smaller level representations, byte pairs. Okay, And the vocabulary will also include, so this so if your vocabulary, they work with a vocabulary of 30k 30k tokens, like 30,000 tokens. And the vocabulary anyways will contain like A and B and C, like all the English characters as part of the vocabulary. Okay, so even if you have a word that you've never seen before, it will still be represented, because we break it down into its components, and the components could be like these characters, or concatenations of them, like this. In any case, you'll get to know more about byte pair encoding and the algorithm that generates them, and how you can actually run the code, and so on. That's what you will get to know in the lab. In this part here, what you are seeing is that you have two sentences, and so you have sentence A, okay, and you have sentence B. And as I said, we need two sentences because we are always going to say, okay, is sentence B a good next sentence or not? Okay, so we need a sentence B. And what do we do? Well, we pass each of these sentences to the model, but we need a way to know that they are two sentences. So we separate them with an artificial token, SEP, for separator. So it's just a token, literally SEP, and we put this token to split the two sentences. We also know that they are two different sentences because we will add some sort of an embedding to each of them. So we call it segment embedding. It doesn't show in this specific illustration, but it will come later. But basically, they put, like, for each token in each of these sentences, they add an embedding vector, and these two embedding vectors are different. So for sentence A, for example, the tokens in sentence A will have like a vector of ones, and the tokens in sentence B, each token will, for example, be added to a vector of zeros. And now these vectors, they are going to be learnable. So for each word, we will have an embedding, and then we will add the embedding vector for each word to this learnable segment embedding, and then when we learn, so these values will kind of change over time, and so on. The overall representation will change. So the idea here is that these segment embeddings are just one way to differentiate sentence A from sentence B. Okay, and I can actually show, this is like a later slide, but really, so you take this word my, for example, and you go to word to vec, for example, and you fetch the embedding vector for it. It could look like this, right? But then you also have a segment embedding vector, which is basically just a vector that's like full of ones. And then you add this one to the segment embedding vector, okay? And then there's actually one more vector that you will add to each word, which is, or each token, which is a position embedding. And we have looked at the idea of positional encoding when we talked about the transformer before. Okay, so basically you concatenate, like you add these three vectors for each token. There is like a positional embedding vector here, and you basically add them together, okay, to get some sort of representation. In any case, we will come back to this slide. I just wanted to show you that there is this positional embedding here, okay? And in this slide, they show that, okay, this is E for embedding, and all the first sentence has E subscript A, and the second sentence has E subscript B, which just to show that this is a different embedding. Okay, a different embedding for like the second sentence. Okay, a different positional embedding. Going back here, let's try to see what else is here. So sentence A and sentence B, and then we separate them with a separator, and we know that for the tokens in each of them, we will add a segment embedding that's a learnable embedding, okay? And then each sentence will have tokens, token 1 to token N for the first sentence, token 1 to token M for the second sentence, right? And then we also add some artificial token here in the beginning. And this artificial token, just think about it as a place filler. We add it and we call it CLS for class. Because when we train the model ultimately, so and we're kind of like, this is the input to the model and we're going this way, okay? When we train the model, this CLS artificial token will have a very good representation. We will call it C for class here. So once it is trained, we can actually use it. It's a summary of the whole sentence. And if we have a summary for the sentence, we can use it for a downstream task, for example. We can use it for doing sentiment analysis, for example, because it summarizes the whole sentence, okay? So that's what this artificial token is for. It's a place filler that's going to learn an aggregate of the representation of the whole sentence. And then we can use the representation in that token to perform to act as the weights that we are going to fine tune on a downstream task. Okay, it's the representation, the learned representation from Bert that's going to be useful for us. Okay. What else do we need to know here? Well, we embed this artificial token, so E of CLS, but then we also embed each token in the first sentence. And E here is just for embedding. We also embed each token in the second sentence, sentence B. We just call it E subscript 1 prime here, okay? That's like also some embedding. And this is embedding, but it's because it's for sentence B, we just like say prime, okay? And we also embed the sentence separator artificial token. Ultimately, our goal is to get a good representation for this CLS token, and we also want a good representation for each of the tokens, other tokens, whatever they are. Okay? Yeah. And then once we do this, we can take this representation, for example, and that's what we will use for next sentence prediction. Okay? While we are training Bert, we will say, okay, I have a next sentence, which in this case, it's this one. Given this representation, okay, that I have learned, is this sentence a good next sentence or not? Okay, does it occur after me or not, right? Now, in a downstream task, really, this representation will be what will be plugged to do sentiment analysis, for example, sentiment analysis, or any other downstream task. Okay. All right. So so that's what we will use as a representation in the downstream task. So we are going to take this C and we will fine tune it. So let's say that I have a sentence that says like, I like pizza. And now I want to, this is a sentence that is in the sentiment analysis dataset. So now I start with this C, and then the representation in C, and then I fine tune it on this specific sentence here, the sentiment analysis sentence, okay? And then I want to predict a label, okay? And in this case, we wanted to predict if the masked sentence B is the next sentence or not. But in the case of sentiment analysis, we wanted to predict if the sentiment is positive or not. Okay, so that masked sentence B is going to be analogous to the label, the sentiment label. Okay, so which is like either positive or negative. Okay, yeah, because we also know that sometimes we have a good masked sentence, so it's going to be like B, and sometimes we have a bad masked sentence, which is going to be B bar. Okay, uh, so when we fine tune Bert, sentence B is going to be analogous to the label that we will try to predict. Okay, and because we use this C token as a representation that we will use to predict whether this is the next sentence or not, we can in the same way use this representation in this token. We apply it on the sentiment analysis sentence, we fine tune it there, and then we use it to predict the label. Okay, so in fact this sentence A is going to be analogous to the input in the sentiment analysis data set. Okay, and this sentence B is going to be analogous to the label in the sentiment analysis data set. So the whole idea is that in pre-training we have a good representation, and this good representation, once we have it, if we were doing a sentence level task like sentiment analysis, we are going to take this representation, and then that's what we are going to fine tune. Okay, and in Bert pre-training, we are learning this representation to predict whether a sentence can occur as a good next sentence or not. So it's like you can think about it as like positive or negative. Okay, so it's analogous to the label in the downstream task. Okay, yeah, and here sentence A is going to be analogous to the input, the sentence in the downstream task. So I hope you can see the analogy here. So in other words, when we pre-train Bert, we have a pair, and the first part of the pair is analogous to something like our input sentences in a task like sentiment analysis. And the second part of the pair, which is like this next sentence, is analogous to the labels, so positive or negative, for example. Okay, going back here, so we have now learned a good representation for this artificial token. It's really a summary of the whole sentence, of the whole first sentence. And now for each token in the first sentence, we have learned a representation. And let's say that this specific token was masked. Okay, and now this is what we are trying to learn. Okay, so we will try to predict which word was here. Okay, same thing, here, like, because sentence B, when we shift to the right, is going to be in the next window, because this is a sliding window, so sentence B is going to be sentence A when we shift one sentence to the right. Okay, so it's also going to have like masked tokens, and we will be trying to predict these masked tokens and so on. Okay, so I hope this is useful. But basically, you can read the text here, but basically this is what the text is saying. And the last thing here is that like we can use this. So if this token was TI, then we will use which was the mask. Then that's what we will try to really predict. Okay. Yeah. Because we will try to know what was this word that we have masked at this point. Okay, so this is the BERT pre-training part. We have already discussed it. There is a fine-tuning part. And the fine-tuning part is really like, okay, once we have pre-trained the model, let's use it for a multilingual natural language inference task, for example, or a named entity recognition task, or a reading comprehension task. Now, maybe you don't know much about each of these tasks, but you just need to know that they are classification tasks. Okay, so named entity recognition is, okay, I give you a word and I say, is this word the name of a city like Vancouver, for example, or the name of so the name of a city here, it's a location, right? Or the name of a person like Obama, or not a name of anything. It's not a named entity at all, for example, right? And so on. So that's like named entity recognition. SQUAD is the Stanford question understanding data set. It's a question answering data set. And basically, what it is that I give you a paragraph and then I ask you questions about it. So I ask you questions about this paragraph. So it's a question answering data set. And the idea is that the answers will come from the paragraph. So the paragraph is running like this, and the answer is this span of the text. So you need to know the start of the span and then the end of the span. And by knowing that, you know the whole span, right? So that's the answer basically. This is why you see like start and end span here. Okay. In fact, and the idea here is that in the fine tuning, we have something that's analogous to the pre-training. Once we have pre-trained the model, then really this part, okay, is analogous to this part. Okay, so this part was the sentence A, and we got a good representation to summarize it. And now this part is going to be our question, okay, and we want to get some good understanding of this question and so on, and then we will use that understanding to find the answer. Okay, yeah, from the paragraph. All right, so this part is a different color. Is analogous to this part. Okay, yeah, and because the answer, so the paragraph here is basically the answer. The answer comes from the paragraph. Okay, so yeah, I hope you can see the analogies. This is sentence A part and this is sentence B part, and sentence A is analogous to the question, sentence B is analogous to the answer. In the case of sentiment analysis, sentence A is going to be analogous to the sentence we want to represent. So I like pizza, as I said before. And sentence B is going to be analogous to the tag, which is like, positive or negative. Okay. Yeah. I hope you can see the analogy. And, for each of these tasks, there is this analogy. Okay. And if the task requires me to have a whole sentence representation, then I'm going to use this C. If the task needs me to get a representation for each word in the sentence, like in the case of named entity recognition, for example, if I have something that says New York City is, so I need a representation for this and for this and for this and for this and so on. It's like a word level representation that I am not looking for a summary of the whole sentence. I'm really looking for a good representation for each of the words, because I want to, so given a word, I want to know if it is a named entity or not, or part of a named entity or not, because these two are a single named entity, right? So in this case, in tasks that involve or that require not a whole sentence representation, but a good representation for each token, well, I can easily just take these representations of the tokens, right? And then I can just plug in them here, right? So now that's what I will do. But I'm always so the thing that I want to learn or get a good representation for is going to be analogous to my first sentence. Okay, this is still analogous to my first sentence. Okay, because that's like what I get a representation for in the pre-training part. So in the fine-tuning part, still is going to be analogous to the first sentence. Okay, so I would suggest that you probably, if you're not understanding this fully, and I've tried to say it in different ways, I would probably suggest that you just like stop the video and then maybe rewatch the previous part. If that's helpful, maybe you already have it clear in your mind and so on. There will be some next slides that kind of like try to support this point of the distinction between pre-training and fine-tuning and so on. But I'm not going to spend too much time on these slides because they have some text, so you can just read the text. Okay. Now, because we talked about this question answering data set and so on, I thought maybe I should just show you the paper. This is a Stanford question answering data set, and it's a large data set and so on. And it's basically given a paragraph or like a passage. Can we answer some questions on it? And let's look here, for example. So this is a passage. And we can construct some questions. This is question 1, this is question 2, and this is question 3. We can construct some questions about it. And this is answer 1, and this is answer 2, and this is answer 3. And note that sometimes the answer is here, it's a single word, but it doesn't have to be. It's a span here, okay? And we need to know the start and the end of the span in order to know the whole answer. And, so this is saying in meteorology, precipitation is any product of the condensation of atmospheric water vapor that falls under gravity. The question here is like, what causes precipitation to fall? Well, gravity. Okay? So that's the answer to the question. So basically you have a passage, or what they call paragraph, in the Bert paper, and then you have an answer to it. Like you can, they asked humans to read the passage and then ask questions, okay, and then answer these questions. So now I have a question and answering data set. This is a question and the answer to the question, and then I can train a model to, given a question, to answer the question for me. Okay. So this is basically, the question is basically analogous to I like pizza. In the case of sentiment analysis, because I need to understand the question so that I can know the answer, right? I can know the answer. In the case of sentiment analysis, I need to understand the sentence in order to know whether it's positive or negative. So, this answer, so let's say this answer here, okay, is analogous to the labels, okay? And this question here is what we need to understand. So it's analogous to the sentence I wanted to understand. Okay? It's just a different task, but it's still like a supervised task because we have the question and we have the answer. Similar to sentiment analysis because we have the sentence and we have the label. Okay? Yeah, just I thought I would show you this because basically in the Bert paper, it's something that they have here, and they have like the question and the paragraph thing and so on. Okay. And now here's something that we kind of took a peek at previously. It's just basically showing us the input to the Bert model. So what we need to know is that there are two sentences. So this is basically the first sentence, and this is basically the second sentence. And the first sentence is my dog is cute. And because we have two sentences and we wanted to separate them, so we put this separator here, right? And then we talked about the CLS token, which is an artificial token that we put here such that we will learn it, and it will be basically a summary of the whole of this whole first sentence. This is what I called sentence A. Okay, this CLS token, once we learn it, it's gonna give us the C, which is the learned representation of the CLS token, which is an aggregate of the whole sentence. It's an aggregate learning of this whole sentence. Okay, now this is supposed to show us that, okay, given a token, we have an embedding for the token, and we have a segment embedding, which is basically a vector of ones for this sentence and a vector of zeros for this sentence. Like for each word, we have a vector of ones here, okay, and a vector of zeros here for each word in the second sentence, just to distinguish the first sentence from the second sentence. And then we have a vector of positional encoding and so on, right? And we just like add this embedding vector to this segment embedding vector to this position embedding vector, and then we get a representation for the CLS class. So that representation will go through Bert. So let's say that now Bert lives here. Okay, so that whole thing, each of these will go through Bert. Okay, each of them will go through Bert, and then we will get some representation. So this one will get a representation we call CLS, and this word will get like a representation T1, and then this one will get a representation, we call it T2, and so on, right? So for each one, like until we have like Tn for the first sentence, and then for the second sentence, will be something that we will also learn. When we shift one sentence to the right, then the sentence B is going to be our sentence A, and then it will also have like these representations that we will try to learn. Okay, so that's it. So that's basically the input to Bert, and that's the type of embedding that we need to add up for each token, and then this is how we pass it to Bert, and then we will learn. Okay, a note, for example, here is that the word playing is broken down into play and ing, and in order to indicate that this ing is not its own word, it's basically some part of a word that was preceded by other characters, then they put like this hash sign here. So that's the byte pair encoding representation. Okay, the masked language model is what we have already talked about. So it's the idea that I have a passage. Let's say even the passage we are looking at here, I could choose to take this word and remove it, and choose to take this word and remove it, and then I put the word mask here, and then I put the word mask here. Okay, and that will be something that they will do for sentence A. Okay, they mask stuff in sentence A, and then sentence B is going to be my sentence A when I shift to the right. So I'm going to also kind of like use it to mask some words in it and so on, in the same way. So how do we do this? Well, we take the sentence and then we pick 15% of the positions, so the indices. So if the sentence had like 100 words, I will pick 15 out of these 100. Okay, so it's going to be 15% out of the 100, right? And then I will mask them. But then there's a problem if I do this, because during training I can do this masking, but then during test there will be a mismatch, because I'm not gonna, like, when you give me a sentence that says I like pizza, I want to get a representation from Bert that will be useful for represent, like when I fine tune it on this "I like pizza" sentence, it's going to be useful. And the words in the Bert sentences like have these masks here, but this sentence doesn't have any masks when I fine tune on it. Then they said, okay, we will still choose 15% of the sentence, and but we will not mask the whole 15%. What will you do? They said, okay, and this is in the next slide, and you can read this slide carefully, but I'm just gonna summarize it for you. They said we will pick 15%. So this was our text, and let's say this word was picked, this word was picked, and this word was picked. Okay, so these are the 15%. Let's pick one of them. Let's say we're talking about this word as one index in the 15%. They said once we pick the 15%, for each index in it, we are going to do the following. 80% of the time, we are going to replace the word with mask, with the token mask. Okay, so replace it with the token mask. Okay, and 10% of the time, 10% out of the 15%, which is basically 1.5%, right? They said we will leave it as is. 10% of the time, 10% out of the 15%, leave it as is. So let's say the word was cute, so they leave it as is. Like I'm just gonna say as is. Okay? And for the remaining 10%, they will just swap the word with a random token. So they will just pick any token randomly. So let's say the word T, and they will put it here. Okay, so I hope this is clear. And by following this procedure, then they will sort of accommodate this idea that during training they do this masking, and during test there is no masking, so there will be mismatch. So to alleviate this problem, they won't really mask the full 15% of the time. They will pick the indices of 15% of the tokens, but then among these 15% of the tokens that they have picked, they will mask 80% of the 15%, and then do not do anything 10% of them, and then swap the word with a random word 10% of the time. Okay, that's what they follow in order to do this masking of the language model. I realize there are some details here, so you can read this passage and then sort of carefully think about the details I have explained. Now, next sentence prediction, this is really a slide that we have already explained. All what they are saying here is that this is sentence A and this is sentence B. And we're going to ask the question, is sentence B a good sentence? Does it really occur after sentence A or not? Then they cast this as a binary classification task, which means that 50% of the time they pick sentence B from the data set. So for example, if this was, so this is, this is sentence, if this is sentence A, this whole thing, for example, right? If I call this sentence A, then this one, this whole one, is going to be my sentence B, because it really does occur after sentence A, right? So that 50% of the time from the Wikipedia dataset they will train on, they will leave the second sentence as is, so it really has to come after the first sentence. But then for 50% of the time, they will just pick random sentence, and they call it, like, let's call it B bar, which is going to be like, can I like fabricate a sentence, like fetch a sentence from elsewhere and just put it here? Okay, so let's say that the first step is useful. Let's say this was my sentence that I picked randomly, and it doesn't really occur after this real sentence. Or let's say, to confuse this thing, is this more, I like apple, for example. How is this sentence really related to sentence A? It's not. So that's really what next sentence prediction is. This is how they cast it to a binary classification task with a good sentence and a bad sentence. Okay, what is the data set they train Bert on? Well, two things. There's a book corpus, that's this one. It's 800 million words, so it's large. And then English Wikipedia, which is 2.5 billion words. So it's 2,500 million words. Okay, so this is very, very large, right? So note that they can't really train, for example, on a data set like this one, the billion word benchmark data set. Why? Because the sentences here are shuffled, and they really need a data set where the sentences are sequential. They are in their ordinary, usual, natural order, because they need to have sentence A, sentence B, and so on, right? So this is useful to have. Okay. Yeah, and they can't do this with a shuffled data set because the order of the sentences is just now random, right? Okay. How do we fine-tune Bert? Well, I think I've already explained this to some extent, not fully, but they are basically saying that, we can plug in the task-specific inputs and outputs into Bert. So Bert had like pre-training stage, pre-training, and fine-tuning stage. We've already talked about the pre-training. Now we are talking about the fine-tuning. And note that the pre-training had two things. It had sentence A and sentence B, right? Now, actually, it's pretty similar to what we will do on fine-tuning, because sentence A, sentence B, sentence A, I can actually say it's similar to I like pizza, which is a sentence that I want to classify. Okay, so it's analogous to it. Now, sentence B, okay, which I asked Bert during pre-training, is this a good next sentence or not? Well, I'm asking this model, is this positive or not, like positive or negative, right? So sentence B is analogous to the tag, right? So I mentioned this before, but since during pre-training, this is what we do, well, during fine-tuning, this is what we can do. It's analogous to it. So we just now plug the inputs and the outputs of the downstream task into Bert, and then we kind of continue training it. Like now we call it fine-tuning, and end-to-end, meaning like there's nothing that we are gonna actually add to this model. We just like take the Bert and then feed the data and the labels from the downstream task to it, and we continue training it. And now we just call it like we are now fine-tuning it, because we are asking it to learn a little bit more about the specific labeled data set for and task. Okay, so they are saying that sentence A and sentence B from the pre-training are analogous to whatever we will be doing in the downstream task. I have given you the example of text classification here, which is what sentiment analysis is, because we have text and we have a label. So that's the text and that's the label. It's a pair, also analogous to the pair of A and B. Okay, let's say that the downstream task was really something else. Like, let's say it was really okay. So we now know that it can be analogous to sentiment analysis, and let's put it aside here. Okay, but let's say that the downstream task was really something like a task like what? Like question answering, right? So we have a question and we have a passage that has the answers, right? So that's going to be like sentence A, and that's analogous to sentence B, which is the answer, right? It's the same thing. Or a hypothesis premise for a task like entailment, right? Um, so for example, this is saying something like saying, um, Julian teaches every day, and then Julian is a teacher. So somebody who teaches every day in school is a teacher. Okay, usually, right? So this is like an entailment. So, the two parts that one of them, one statement entails the others. Okay, and any other task. So the first part will be analogous to sentence A, and the answer or the label we are asking for is analogous to sentence B. Let's say that I was doing a task like sequence tagging, like named entity recognition. Again, like something like New York City is, right? Well, I always have like, is this like, what is this? What is the tag for this, right? Right? So we're always asking. So this part is going to be analogous to sentence A. The answer to it, or the tag, is analogous to sentence B. Okay? So I hope this is sufficiently clear. Okay? And for this purpose, when we do something like sentiment analysis, this is like we need a representation for the whole sentence. So we use the C token, the trained C token representation from Bert, as I explained before. But if we are doing something like New York City is, as I also said before, I will use the TI, which is a representation for each of these tokens. This, like, Bert gives me a representation for each of the tokens, so I will use it from Bert. That's what's going to be fine too. This is what basically this part is saying. Okay. Finally, they show some results. So they compare the model to a bunch of previous models. This is a model that's like a previous state of the art from OpenAI. This model is basically Elmo, which we have seen before, but it's even further enhanced with attention and downstream task related by LSTM. This model is another model from OpenAI, is called GPT-2, which we will actually be looking at in the probably in next week. And these are the two Bert models, and they compare the two Bert models to all these models, and they show that Bert is consistently better on all the tasks, really. And these are multiple tasks. So I'm not going to talk about what exactly these tasks are, but you can get a task like natural language inference, or something like sentiment analysis, for example, and so on, right? And they show that really Bert exceeds a lot of these other models with really a big margin. Look here, like this is 60.5 versus the best other model, non-Bert model, is 45, really. So this is really a huge margin, right? Or look at this one, for example. It's kind of a little bit less than 10%, right? So it's still a huge margin, right? So in any case, so this just shows that Perth is pretty powerful and it's pretty useful, and it's a good model that you should be happy that you now know how it is trained and so on. And then you are going to also learn how to engineer it, how to use it to on a downstream task. So I hope you have found this useful. Yeah, that's the end of